So the ultimate goal for this video is for me to show you how to determine the intermolecular attractions that molecules will experience and how that leads to specific characteristics of them that you might see in your everyday life. But in order to do that, we need to figure out how we determine if molecules are polar or nonpolar. And in order to compare whether a molecule is polar or nonpolar, in order to determine that, we need to know what electronegativity is, because we need to compare the electronegativities of their elements. So the electronegativity of an atom is a measure of its attraction for electrons. So as you move across the periodic table, remember we had talked about trends in general during first year chem. So as you move across the periodic table, the number of protons increases, which means that the electronegativity is going to increase as well. As you move down the periodic table, however, since your atoms become bigger and bigger because they have more principal energy levels, your electronegativity is going to decrease. And so this table shows that as you move up the periodic table and across to the right, electronegativity increases, which tells us that the most electronegative atom that exists is fluorine. Okay? So why does that matter? Well, that helps us to determine if a bond is going to be polar or nonpolar. So if a bond is nonpolar, what that means is that the two elements that are sharing the electrons in this covalent bond are going to have the same electronegativities. So there's going to be no difference in electronegativities, zero difference. Therefore, they're going to be sharing the electrons equally, causing the bond, the covalent bonds, to be nonpolar. If instead there is a slight difference in electronegativities between the elements, like for example here I have hydrogen and chlorine. Since chlorine is slightly more electronegative than hydrogen is, what that means is chlorine is going to hog the electrons towards it, and therefore the bond itself is going to be polar. Okay? And we represent that with the dipole, so you would have an arrow pointing towards chlorine to demonstrate the fact that chlorine is hogging electrons towards it. So therefore it will have a partial negative charge because it has a greater cloud of electrons, as you can see in that purple diagram there, than the hydrogen does. Now, if the difference in electronegativity is extreme, which would be the case if you have a metal and a non-metal, right? Metals have a very low electronegativity, non-metals have a very high electronegativity, then the atoms no longer are able to share because there is such a difference in electronegativities, then the non-metal is actually going to steal the electron, and you have now an ionic bond, which we'll look at in a second. So why do I care about bond polarity? Well, bond polarity, if you have bonds that are polar, then we can use that information to then determine if a molecule is polar. So if a molecule is nonpolar, what that means is that the dipoles, remember the dipoles are representing pulling of electrons. So here for carbon dioxide, since oxygen is more electronegative than carbon, you're going to have arrows going out towards oxygen. Since those dipoles cancel though, imagine it's like a tug of war, that molecule is going to be nonpolar. Same thing with CCl4. Notice chlorine is more electronegative, but it's going to be pulling up and then to this three ways down. Imagine in a tug of war, that thing's not going to move. And a better way of saying that, we don't say it doesn't move. In chemistry, we simply say the dipoles cancel. And therefore, those two molecules are nonpolar. For polar molecules, the dipoles do not cancel. So if you look at HCl, for example, chlorine is more electronegative, so you have the arrow pointing towards chlorine to represent it hogging the electrons, but there's nothing to counteract that pulling on the other side, therefore that molecule is polar. Similarly with NH3, since nitrogen is more electronegative than hydrogen, you have those arrows pointing towards nitrogen. However, since nothing's pushing downwards, that molecule would move in a tug of war or whatever battle you want to imagine. And so the way that we describe it is we simply say that the dipoles do not cancel. So why do we care, right? Why do we care if a molecule is polar or nonpolar? Well, that will allow us to determine if that molecule what type of intermolecular force it experiences. Okay, so the first type of intermolecular force that every single atom and every single molecule experiences no matter what is dispersion forces. So what happened in dispersion forces is electrons normally float around randomly. They move around. We tried to predict, approximately where they are by using our electron configuration, but ultimately it's very hard to predict. However, if those electrons happen to match to line up. As you can see for the second diagram on the right hand side, you see those 3 electrons there. They're towards the right hand side of that atom. Okay, that will cause a temporary dipole, a partial negative charge. That partial negative charge will then repel electrons from a nearby atom, causing the atom next to it to have a partial positive charge where it's closest to that partial negative. And that partial negative, partial positive, we call it a temporary dipole, and that is your dispersion force. So anything that has electrons can create that temporary dipole, can have those dispersion forces. So we call them London dispersion forces. Now, because they are temporary, these are our weakest type of intermolecular force. You will see sometimes it can be stronger if you have a ton of electrons, which I'll talk about in a second, but it tends to be the weakest attractive force. But everything has it. Now, if you have dipole-dipole forces, that is because you have a polar molecule, okay, and you will therefore, for any polar molecule, you'll have one part of that molecule that's partially positively charged and one part that is partially negatively charged permanently, right? And therefore, if they line up, 2 different molecules line up, as you can see for HCl, the Cl, that is the partial negative charge right there. Hydrogen has that partial positive charge. That attraction, that is a dipole-dipole force. But note, it can only happen if you have a polar molecule. So if you have a molecule that is nonpolar, the only force it can experience is a London dispersion force. But if I have a polar molecule, it can experience dipole-dipole forces. The last type of intermolecular force is hydrogen bonding. Now, hydrogen bonding is a type of dipole forces, is a type of dipole-dipole force, but in order to have hydrogen bonding, you've got to have a hydrogen. So if you look at NH3, for example, you have a hydrogen. It has to be bound to either fluorine, oxygen, or nitrogen. So in all 3 of these examples, you can see that the hydrogen is bound to nitrogen, oxygen, or fluorine. And then you've got to have another nitrogen on the nitrogen, oxygen, or fluorine on the other molecule. And that attraction between the hydrogen of one molecule and the nitrogen or the oxygen or the fluorine of the other molecule, that is a hydrogen bond. So for example, I wanted to show you really quickly a case where you don't have hydrogen bonding. So here's this molecule right here. Okay? The hydrogen on the right-hand side that is covalently bound to the oxygen, that can form hydrogen bonds. You would need another molecule close to it with either oxygen, fluorine, or nitrogen, but that can perform hydrogen bonding, absolutely. However, the hydrogens on the left-hand side that are chemically bound to the carbon, since those are not chemically bound to fluorine, oxygen, or nitrogen, those cannot perform hydrogen bonding. Okay? So let's really quickly compare the strength of our intermolecular attraction. So if you start at the bottom, dispersion forces tend to be the weakest, and I'll show you some examples where that isn't the case. But dispersion forces tend to be the weakest because they're temporary, then dipole-dipole, then hydrogen bonding. Now notice these are intermolecular forces, so I would note that in your notes. These are intermolecular forces, meaning they are between at least 2 different molecules. We also talked during first year chemistry about ionic bonding and covalent bonding. When you have ionic bonding and covalent bonding, that is within a molecule, okay? So ionic bonding is between a metal and a nonmetal, and covalent bonding is between 2 nonmetals. So your intramolecular forces, which those are always going to be stronger than your intermolecular forces, which are between different molecules. Okay? So this begs the question, okay, what's the difference between inter and intra, and how am I going to see these in everyday life? Well, as I just said, intermolecular forces are between 2 different molecules. Therefore, if you ever melt something or freeze something or boil something, the change that's occurring, that is a physical change. And in a physical change, you are going to be breaking intermolecular attraction. So for example, when I melt ice, I am breaking the hydrogen bonds that exist between water molecules. Okay? When I vaporize water, I am breaking the intermolecular attractions. I'm breaking the hydrogen bonds there. Okay? One thing to note, when you are going from a solid to a liquid versus a liquid to a gas, it requires a lot more energy to go from a liquid to a gas. And the reason why, now you can understand it. When you go from a liquid to a gas, you are breaking all of the intermolecular attractions that exist between those molecules, right? Because gases are not attracted to each other, or at least we assume that they're not. When you're going from a solid to a liquid, yes, you are breaking some intermolecular forces, but you're not breaking all of them, right? So in order to go from a liquid to a gas, it requires much more energy than simply going from a solid to a liquid, right? When you have a chemical change, when you are changing the identity of the substance, you are actually breaking intramolecular forces. So for example, if I have sodium oxide and it decomposes to form sodium and oxygen, I am breaking the ionic bonds between sodium and oxygen. If I am breaking up water to form hydrogen gas and oxygen gas, water, those are covalent bonds that I have to break in order to form hydrogen gas and oxygen gas. So you are breaking intramolecular forces. Okay, fine. But how can we actually compare the strength of intermolecular forces in the lab? How is that possible? Well, what we look at, what we can actually measure in the lab, are the boiling point and the melting points of specific substances. By determining at what temperature something melts or something boils, you can determine the strength of intermolecular forces or intermolecular attractions. And the reason why is because the stronger the intermolecular force, the higher the boiling point or the melting point will be.
So as I had just mentioned, dispersion forces tend to be the weakest type of intermolecular force. Dipole-dipole is slightly stronger, and then hydrogen bonding is slightly stronger than that. And again, just as we stated, the way that we determine the strength of the intermolecular force is by looking at the boiling point or the melting point of a compound. Now, there are some exceptions that we need to talk about. So if both molecules that you're looking at have the same type of intermolecular force, then how can we actually compare their strengths? Well, if both of the molecules have London dispersion forces or both molecules have dipole-dipole forces, what we then do is we compare the number of electrons. And the reason why is that the molecule that has more electrons, it is going to be more polarizable, meaning its London dispersion forces are going to be stronger because it has more electrons that can actually line up to create that temporary dipole. So the more electrons a molecule has, the more polarizable it is because the more of a partial charge that can form, okay? And therefore the stronger the intermolecular force. So if you have two molecules with the same intermolecular force, either London dispersion or dipole-dipole forces, then we simply compare the number of electrons in order to determine which has a higher melting or boiling point. Well, what if both molecules have hydrogen bonding? Then what we do is we compare the number of possible hydrogen bonds. So if a molecule, let's say, for example, we're comparing two molecules, they both have hydrogen bonding, okay? And one molecule has one nitrogen and the other molecule has two nitrogens, then the one with two nitrogens has two different possible locations for hydrogen bonding. And therefore, since it can form more hydrogen bonds, it's going to have a stronger intermolecular force than the one that can only form one hydrogen bond. Now, that being said, if they can form only the same number of hydrogen bonds, right, if both can only form one hydrogen bond, for example, then we go back to the way of comparing it if they had the same type of intermolecular force, which is by comparing the number of electrons or comparing their polarizability, okay? Last little quirk with this. What if, for example, you were looking at two molecules and one molecule has London dispersion forces and another molecule has, let's say, for example, dipole-dipole forces or hydrogen bonding? Is it ever possible for the molecule with London dispersion forces to have a higher boiling point or a higher melting point? And the answer is yes. A molecule with London dispersion forces can actually have stronger intermolecular attractions than a molecule that has dipole-dipole or hydrogen bonding. And the way that that happens is if the molecule with London dispersion forces has so many electrons that it is extremely polarizable, this could cause it to have a higher boiling or melting point than a molecule that's smaller, that has fewer electrons and has dipole-dipole forces or has hydrogen bonding. So just as a quick recap, traditionally, what we normally see, London dispersion forces are the weakest type of intermolecular force, followed by dipole-dipole, right, which is slightly stronger, and then hydrogen bonding, which is the strongest. If you're looking at two molecules that have the same type of intermolecular attraction, so dipole-dipole, or both have London dispersion, then we compare the number of electrons. The molecule with more electrons is more polarizable, and therefore its intermolecular force is going to be stronger. If you're comparing two molecules that have hydrogen bonding, if they have different numbers of hydrogen bonds, meaning one has, for example, 1 nitrogen versus 2 nitrogens, or 3 nitrogens versus 5 nitrogens, the one that can form more hydrogen bonds is going to have the stronger intermolecular force. If they can only form the same number of hydrogen bonds, then we go back and we talk about which one has more electrons. And then finally, just because a molecule has London dispersion forces, because it's nonpolar, doesn't mean that it's going to have the lowest boiling point or melting point. If it is a large enough molecule and has enough electrons, if it is that polarizable, its intermolecular force can be stronger than dipole-dipole or hydrogen bonding.
Okay, so let's look at some practice problems. So let's compare the boiling point for each of the following. And we need to make sure to reference the intermolecular forces that they experience. So I'm going to compare HF and HBr. Well, HF experiences hydrogen bonding, and HBr experiences dipole-dipole attractions. So since HF experiences hydrogen bonding, which is stronger than dipole-dipole forces, HF, hydrofluoric acid, is going to have a higher boiling point. Okay, not too bad. Let's compare a potentially more difficult one. So O2 versus N2. O2 experiences LDF, N2 experiences LDF. Well, hold on a second. How can I compare two that have the same intermolecular attraction? Well, if both molecules have London dispersion forces, the way you compare their strength is by looking at their number of electrons. The more electrons a molecule has, the more polarizable it is, meaning its electrons if it has more electrons, you're going to have a greater lining up of electrons potentially that could cause a bigger temporary dipole. And so therefore, when you're comparing LDF, if you have two molecules that only have LDF, you look for the one with more electrons. So I would say O2, because it has more electrons, it's more polarizable, making its London dispersion forces stronger and giving it a higher boiling point. So those are some key buzzwords for AP that you need to make sure that you remember. Number one, it has more electrons. It's not that it's bigger, it has more electrons, and therefore it's more polarizable. Okay? So let's compare CH3OH and CH3CH2 all the way OH. All right, so both of these molecules, since they are polar, right, and they have hydrogen bound to an oxygen, they both have hydrogen bonding. Well, great. How can I compare them? Well, in addition to hydrogen bonding, they also experience LDF, because notice for each of these explanations, for HF, it's not only that it has hydrogen bonding, it also has LDF. And for HBr, it also has LDF. So these have hydrogen bonding and LDF. If I compare the strength of their London dispersion forces, since the second molecule has more electrons, it's more polarizable, and therefore it's going to have a higher boiling point. Okay? So if it's that one has LDF and one has hydrogen bonding, it's obvious. But if they both have the same type of intermolecular attractions, right, hydrogen bonding and LDF, then you're going to compare them based on the strength of their London dispersion forces. Okay, because the bigger molecule is, the stronger its London dispersion forces are. All right, let's look at the last one. I give you those two molecules there. If you notice, the first molecule has two OHs, while the second one only has one OH. So while they both have hydrogen bonding and London dispersion forces, they're pretty similar in size. So it's not the London dispersion forces that we're concerned about. It's the fact that the first molecule can form more hydrogen bonds than the second one can. The second one can only form one hydrogen bond for each molecule. So while they both experience hydrogen bonding and LDF, the first one can experience more hydrogen bonding, and therefore its intermolecular force is stronger, and therefore it has a higher boiling point. Okay? So ultimately, yes, London dispersion forces tend to be weaker than dipole-dipole, which tend to be weaker than hydrogen bonding. However, if you have the same type of intermolecular attraction, compare size, because it's likely that London dispersion forces are at play. If you have the same type of intermolecular force and it's hydrogen bonding, first make sure that one of them doesn't have the potential to form more hydrogen bonds than the other one does. Okay, so you guys have your own practice that you get to complete in order to make sure you really understand this.